Welcome back to Gate Baba. In this lecture, I am going to teach you the complete information of pattern and allowances, the complete top to bottom information of pattern, right? So, how do we define pattern? Pattern is the replica of the object to be made. In many textbooks, up to here only written, but it is absolutely wrong. We have to add some extra line also, that is with some modifications. Pattern is not the exact replica. Pattern is not the exact replica of the object to be made. It is going to get some allowances and some. We have to remove the core prints of the pattern, and we cannot produce some fine details in the pattern. That's why after solidification the part is taken out and some machining operations are done on it to get some required surface finish or some accuracy. That's why pattern is not the exact replica. So pattern is the replica of the object to be made with some modifications. Please make note it, right? So what are those modifications? There are three main modifications. We have to make sure that while designing the pattern. The first one is allowances. We have to use allowances for the pattern. We have to trim off the core prints and we cannot produce fine details. So that's why with eliminating the fine details, we make a pattern. After solidification, we will do some machining operations to get these fine details. So don't worry. So first come to the first point, that is allowances. So what do you mean by allowance? Allowance in the name itself indicates we are allowing the pattern to change of some dimensions. That is what allowance, right? So we have mainly five types of allowances. Sorry, what are those? Shrinkage or contraction allowance, machining or finishing allowance, draft or taper allowance, shake or wrapping allowance, distortion or camber allowance, right? In these five allowances, these first three are categorized as positive allowance, and the shake and wrapping allowance is categorized as negative allowance, and the last one is also called as zero allowance. So what is the difference between positive, negative and zero? Have you ever imagined? I will make it clear, very clear, because in GATE exam many times question asked from allowances. That's why we have to make sure we learn each and everything, right? Positive allowances means adding of material. Adding of material to pattern. This is what positive allowance. If we add material to pattern, then it is called positive allowance. Why to add material? We will discuss that later. And if we delete some material from pattern, we delete from pattern. If we delete material from pattern, then it is called negative allowance. If the pattern is made exact size of the casting, then it is called as zero allowance, right? If the pattern is oversized than casting, then it is called positive allowance. If the pattern is undersized than casting, then it is called shake or wrapping allowance. If the pattern is made exact size with the casting, then it is called zero allowance. Okay, please remember this. And then first come to, I will start from the last. First, distortion allowance. Distortion allowance is not required for each and every casting. It depends on L/T ratio. Here I have given a nice diagram. For example, I am planning to cast a material that is having a U shape, extruded U shape, right? This is the casting that I want to produce, right? For example, this length is L1, we can see here, and this length is L2, right? If L1 is greater than L2, definitely area of 1 is greater than area of 2. Yes or no? Definitely. because, for example, assume a sand casting. The sand is on this surface, and also present in here also, right? The main mode of heat transfer here is conduction. Main mode of heat transfer is conduction. We know from conduction equation, heat loss is equal to Ka dt by dx, right? Dx means thickness of wall. This is the thickness, and it is constant. It cannot be changed. Conductivity of the material, that is also constant. Temperature difference. This surface has same temperature as this surface, so temperature difference will also be same for this portion and for this portion, right? Then what is changing here? Area is changing. Here the area is high and here the area is less. Let me pick another color. This surface has less area than compared to this surface. So definitely heat lost on this surface will be high. So what will happen? If it is losing heat faster rate than this, then it will shrink definitely, and it will shrink slowly somewhat than this surface, right? So if the shrinkage is non-uniform, then the final product may become like this. So the main reason of distortion elements, giving distortion elements, is non-uniform shrinkage, right? Now you understand what do you mean by non-uniform shrinkage and where it come from. It is the fundamental phenomenon of conduction heat transfer. Okay, if the areas are not the same, then the heat transfer is also not same, then shrinkage is also not same. So to make sure that we are not giving any allowance, then it will become like this. So how we design the casting? It's a simple technique. Just make the pattern like this, right? Just make the pattern like this. Now allowing it to solidify there. After solidification, what will happen? This surface has higher surface area, we know, because length is more. So it will shrink. After shrinking, it will come to exactly this shape. That is what we required, right? By the way, this is not required for each and every pattern. For lengthier and thick patterns, thick castings, it is required. For only thick castings, it is required, right? And next come to the shake or wrapping elements. This is due to human errors only, because we cannot exactly pick up the pattern material from the mold cavity without shaking our hand, or by some manufacturing defect. What we can do, right? So if we want 100 mm casting, 100 mm length on one side, for example, take a cubical shape, right? Take a cubical shape, each side having 100 mm length. If we want 100 mm length, if we make the pattern as 100 mm, what will happen? By removing the pattern material, the sand also somewhat disturbed, right? And the cavity size may increase. So to make sure that we are producing exactly 100 mm, we make the pattern as 98 mm only. If it is 98 mm, by removing the pattern from the mold, the next dimension will come with our shaking movement will be 100 mm, right? So what we are doing here, we want exactly 100 mm, and we are deleting some material from the pattern to make sure that we get 100 mm. That's why it is negative elements, right? You can see here, we are not adding any material, no adding and no deleting material. So that's why it is called zero elements, right? But here we are deleting some pattern, that's why it is called negative elements, right? And then next come to draft elements. Draft means it is provided for vertical surfaces only, and this is for high height surfaces. High height castings, right? To avoid continuous contact between sand and the pattern, we made the pattern material as this shape, right? We make the pattern as like this. Think it in other way. If I make the pattern as like this, assume sand is over here, over here, over here, over here, over here. In the mold, sand is here, right? Everywhere is sand. The first contact point is here, right? If I want to remove the pattern, I just lift it up. What will happen? The contact area is getting decrease while going upward, right? If I exactly do the job by this shape of pattern material, what will happen? This is the pattern. If I lift it up, there is continuous contact between the mold surface and the pattern surface. So some surface finish and accuracy issues will come up. To make sure that we are not damaging the mold cavity surface, we will provide from some draft allowance. So that is what draft allowance, right? And here also we are adding some material. That's why it is called positive allowance. Generally the draft angle is half degree to 2 degrees. Remember this thing. And it is only provided for vertical surfaces. Clearly I said this. And then next come to machining allowance. This is the important one. One time GATE asked this question. So what do you mean by machining allowance? It is nothing but to remove the impression of sand grains from the casting material. We do some machining operations after casting is done. So this is the post machining allowance, that is post machining operation. After getting the casting product, we are taking the casting product into some machining area and we'll remove some of the area of the casting product, right? For example, if I want 100 mm casting, if I make the pattern as 100 mm, let us say, what will happen? Due to sand impressions, I have to remove those sand impressions so that I will machine its surface. After machining, what will happen? The dimension will come to 98 mm for an example, right? 98 mm. But I want 100 mm. So how to get 100 mm? Make the pattern material as 102 mm. Make the pattern dimensions as 102. Then after machining, it will come to 100 mm. That is what I required. Okay. Here there is a simple logic and a simple silly mistake that people do. I will tell you. For example, take a rectangle box here, right? Okay. Make this dimension as, for example, 100 mm, right? So I am adding some material. That means this is the casting that I want to produce. Now I am designing the pattern. The design of pattern will come like this. I am adding some material on both sides so that the dimension will change by 2 mm. This is 102 mm. I am making the pattern machining allowance as 2 mm. So 1 mm, sorry. 1 mm on each side, right? I'm assuming this value. That's why I'm increasing 1 mm on both sides. So this is the pattern dimension. This is the casting dimension. So for external surfaces, it is right, absolutely correct. But if I have a hole in the casting, for example, this is the casting product that I want to produce. This has a dimension of 100 mm. The diameter of hole to be produced is 50 mm, right? What are the pattern dimensions to make this? The pattern dimension of external surfaces must be increased. That means 1 or 2 mm. The length of pattern is 1 or 2 mm. But when come to size of hole, what we are telling here, adding material to the pattern. That means it is a positive elements. So if we add material, what will happen? The diameter of hole will get reduced. We are adding material here also because we put a core inside the mold cavity to get the hollow shape. So that means the core is in contact with the hole. So there must be some sand impression produced on the internal side also. So some internal machining also has to be done. That's why we have to machine the surface. If we have 50 mm size, if we machine that, what will come? 52 mm hole will come. But I am not in intention to get this 52 mm. I want 50 mm only. So to make sure that I will give 48 mm only. So, see, very good point. Here it is 100 mm. It is increased to 100 mm, but the hole size is getting reduced to 48 mm. This is the key point. This is the key point that I want to tell you. This is the key point. The hole size will get reduced, and then the external dimension will get increased. Right? Please make note this. Very important. Many people doing silly mistakes here and losing marks. And then next come to the king of elements. That is nothing but shrinkage or contraction elements. Yes, this is the king of elements. This has in-depth concept in it. Why the material will shrink on different stages, that is mean liquid stage, solidification stage and solid stage. I will explain it very clearly. So let me draw a diagram. So why material will shrink? We know that liquid density, the density of liquid is less than the density of solid. Can you agree with that? Right. But this is not the concept. This is bakwas. Here it will not work. Somewhat it is correct, but here it is not the correct explanation to do this. Right? We are dealing with molten metal. That means it is at very high temperature. The temperature of molten metal is very high. That means it is having very high energy. At high energy, molecules will occupy more volume. Why the molecules occupy more volume? Because of intermolecular vibrations. Intermolecular vibrations. Because the molten metal having high energy, so the energy, thermal energy is converted into kinetic energy, so that molecules will vibrate. Due to these vibrations, the gap between the molecules will increase. For example, this is the initial state, that is at room temperature. After giving high heat, it will come to this shape like this. So these vibrate to and fro. So definitely these when compared to these molecules occupy more volume. That's why on liquid has high volume when compared to solid. So after solidification, definitely this will come again to this shape. So that's why the dimensions will get reduced. Dimensions will get reduced. That's why we have to give some shrinkage elements. Okay. So what are the three stages that these things may happen? Make it as pouring temperature, and this temperature, this is the graph between temperature and time, by the way. This is also called as cooling curve. This temperature is called freezing temperature or solidification temperature, and then this temperature is atmospheric temperature, that means room temperature. This is the direction of this graph. We are cooling the molten metal, that's why the direction is towards down. If it is heating, then the direction may get reversed, right? So there are three modes of heat transfer takes place. Three types of heats are available here. The first one is liquid. This is the liquid zone up to here liquid zone, and this zone is called solidification zone. And this zone is called solid zone. This is completely solid, this is completely liquid, this is partial solid and partial liquid, right? Here the heat given to this material, heat lost by this material, is latent heat. The heat in these two stages is sensible heat because of temperature difference. Here the temperature is constant throughout the process. Temperature is constant throughout this process, right? During solidification, the temperature is constant, right? So here the density will get reduced on cooling, get increased on cooling. That means volume get reduced. Here also volume get reduced. Here also volume get reduced. So for both of these we cannot provide pattern, right? These two things can be maintained by riser design. And this solid zone, our main intention, for this solid zone we provide pattern. The pattern is required to compensate for the solid shrinkage, not for the liquid and solidification shrinkage. Liquid and solidification shrinkages can be compensated by riser design, providing riser, right? The solid shrinkage can be compensated by pattern only. Please make sure that only solid shrinkage, again I'm telling, the liquid and solidification shrinkages are compensated by riser, and the solid shrinkage is compensated by pattern. Okay, if we see the riser design, just look it into riser design, we can observe that volume of shrinkage has to be less than riser volume. Otherwise, how the riser will compensate for the liquid shrinkage or solidification shrinkage? By the way, the riser shape, for example, this is the casting that I want to produce. The riser is placed above the casting. After filling the mold cavity, riser also get filled. If the mold cavity get contracted like this, the riser fluid will come down and fill this gap, right? If the volume of this thing is higher than the riser volume, the shrinkage cannot be avoided. That's why the riser volume has to be greater than the shrinkage volume, or volume of shrinkage has to be less than the riser volume, right? So riser will compensate for liquid and solidification, both shrinkages. Pattern will take care of solid shrinkage. Different materials shrink differently, right? So some of the values I have collected, I will show you in 1 minute. Wait up to that. For examination, you have to remember these golden points. The first point is volume shrinkages are given in percentage of volume. Volume shrinkages are given in percentage of volume shrinkage, and the solid shrinkage is given in linear dimensions, right? Linear dimensions, that means per meter length, like that. So solid will contract to 1 for 1 meter length if it is given as 1 as a value, right? It is given as 10, the solid will shrink 10 over 1 meter length. For 2 meter it will shrink by 20 for 3 meter it will shrink by 30 for 4 meter it will shrink by 40 So if we increase the length of the casting, the shrinkage value will also increase, right? This volume shrinkage is given both for liquid plus solidification, right? The first one will be linked to this and the second one will be linked to this. Okay, for example, I have given values of, let us assume, liquid shrinkage as X%, solidification shrinkage as Y%, and solid shrinkage as Z%. Here I am giving the percentage also. Sometimes examiner will give percentage, sometimes he will give in linear dimensions. So don't confuse. Here I am taking the percentages because most of the times GATE exam asks in percentages only. First question that come from this is, what is the total shrinkage when X%, Y% are given? X means liquid shrinkage, Y means solidification shrinkage. So what is the total shrinkage? What is total shrinkage? The total shrinkage is equal to X% plus Y%, right? The second question, what is the total shrinkage when X%, Y%, Z% are given? These 3% is given. And what is the shrinkage? You have to first make sure that find the total shrinkage associated with these both. That means X% plus Y% and multiply with Z% to get the total value. Sometimes examiner directly give these 2% as some, let us say A%. Examiner may give directly as A% for combined result. Combined result he may give A% also. Then you do A% times Z%. That is the total shrinkage associated with the pattern, right? Here are the sum of the values of the pattern shrinkages. This is the bismuth. For bismuth you can neglect the shrinkage. For cast iron on solidification it will shrink by 10 per meter length. For white metal after solidification it will shrink by 5 per meter length, and aluminium will shrink by 13 per meter length. And the most important objective question, brass. Brass has highest solidification contraction than any other material. It will shrink 23 per meter length. If you want to make a 10 meter length casting, then it will shrink by 230 That is approximately 1/4 of meter. Very huge. We get large error if we design the pattern as exact shape of casting. So we have to make sure the pattern is oversized in this, very oversized. Then only we can get the exact casting that we want to require, right? For copper it is 17 per meter length, and for the steel this is also important one. Steel it is 20 per meter length. This is the next brass. If you look into the liquid or solidification contraction, the highest value for aluminum only. This is the maximum value. it will shrink by 6.5% of volume shrinkage. So you have to make the riser volume greater than 6.5% of volume shrinkage. Then only you can compensate for the shrinkage, right? For the overall, the shrinkage will be higher for steel. This is also good objective question. For the overall, for just a shrinkage, solid shrinkage, it is higher for brass and next steel. But for when we consider overall shrinkage, it is high for steel, right? Please remember this thing. For example, in examination, the shrinkage value of steel or something material is not given. Then what you do? Then he must give the thermal coefficient of linear expansion. That is nothing but alpha. From the thermal stresses and strains concept from mechanics of solids, the thermal strain is equal to minus alpha times change in temperature, right? Strain means change in length to over length, total length. That means minus alpha times t. So what is the change in length? Minus L alpha t. So this is the shrinkage value we get, mm per meter, right? For different materials, alpha will be different. For steel it will have some value, for cast iron it has some value, for aluminum it has some value. So alpha decides the shrinkage value, right? If in exam he will not give the direct values of 17 or 20 or 23 mm, then he must give the alpha value. Then only you can calculate the shrinkage value. After that you design the pattern. And there is another relevance also I want to share with you, that is double shrinkage allowance. When it will come into picture, I mean, there are so many pattern materials that we can work with. Example, we can take the pattern material as wood or steel or cast iron or aluminum or plastic, many materials. If I want to make a standard pattern to work with greater than 2000 times the same pattern, then I must choose the steel or cast iron pattern. So how can I produce the steel or cast iron pattern? By casting only. If I choose the casting method, I must choose the pattern also. For these casting, I required a wood pattern. That means I am using wood pattern to make the steel pattern, and the steel pattern or cast iron pattern is used to make the required casting. So here we are taking the wood pattern and producing the steel pattern. By steel pattern we are producing the casting. So the process will be like this: wood pattern to steel pattern, steel pattern to casting. For example, I want to produce a casting of 100 mm size, right? So take a casting material as, for example, cast iron. I want to cast the cast iron. I know the cast iron shrinkage value is 10 mm per meter length. That means it will shrink by 1 mm per 100 mm length. That means I have to make the steel casting greater than the 1 mm, that 100 mm. That means it will have to make as 1 or 2 mm. Then only I can, after solidification, I get the 100 mm size. If I want this 1 or 2 mm size, I know that steel casting has the shrinkage value as 20 mm per meter length. So 1 or 2 mm, this one. So wood pattern size has to be increased than this 1 or 2 mm, because on solidification of steel it will contract. We know the contraction is 20 mm per meter length. To make sure that, we have to increase the length of wood pattern as greater than 1 or 2 mm. Greater than 1 or 2 mm. I am not particular about the dimensions and calculations, so I am just giving you the information. This is the double shrinkage allowance, right? and the wood pattern is called master pattern, and the steel pattern is called pattern only, and this is casting that we want to produce. So we are using the wood pattern to produce the steel pattern, and the steel pattern is used to produce the actual casting. This is the meaning of double pattern and double shrinkage allowance, right? And this is also a positive allowance. So I am giving you some of the materials of pattern. These are the general pattern materials. Wood, metal means metals and alloys, aluminum, cast iron, steel, brass, etc. Then come to plastics, wax, and mercury, right? Basically, the selection of pattern materials will depend on three major factors. Those are size of pattern, size of casting that I want to produce, and the number of castings that I want to use the pattern, and the accuracy required. For high accuracy and fine surface finish, we use metal patterns, definitely, and for more size also we use wood pattern only. The number of components to be produced will, if increases, we choose the metals, right? I have given some table information also. We will see this later. Then come to plastics. There are so types of plastic materials: polystyrene, foam, PVC, and thermocol. There is a special thing about this. These will evaporate if the molten metal is in contact with this pattern material. So there is no removal of pattern from the mold cavity. Directly the molten metal is poured on the pattern. The pattern gets evaporated and converted into foam. So there is no removal of pattern material. That's why it is called cavityless molding or full molding. We will see this very clearly in later on oncoming lectures. So don't worry. So here we are not producing any cavity with the pattern. We just place the pattern there and pour some sand around the pattern. After that we pour molten metal on the pattern itself. The pattern will get evaporated. So there is no issue in the shrinkage values or something. If I choose the wax material as a pattern material, then it is called investment casting. Very important one. If I choose the mercury as a pattern material, it is called mercast process. By the way, the melting temperature of mercury is minus 38 degrees Celsius. So very rare applications we use mercury as pattern material. And then come to type of patterns. There are mainly 7 to 8 types of pattern types. I said it earlier. If you want to produce a flat surface, there is no need of split piece patterns. We just use a solid pattern or single piece pattern. If you want to produce the 3D surface, not the flat surface, here the 3D surface, this is a 3D surface, then we have to use split piece pattern. There is no other alternative. So the patterns are matched, upper pattern and lower pattern are matched with the dowel pins, right? And then loose piece pattern. This is used when projections and undercuts are present in the casting. And then gated pattern. With this gated pattern, there is no need to cut the gating elements like runner and gate. No need to cut runner and gate. We just cut riser only, right? And then match plate pattern. This is only used for complex shapes and for mass production. And that's it. Then sweep pattern. Sweep pattern is the important one. With the 2D pattern, we are producing 3D cavity. Just take a rectangle board and place it inside the sand and revolve it around its axis. What will happen? It will create a cylindrical shape. That means it is creating a 3D cavity, right? If I place this is my pattern and this is the axis. If I revolve this around this axis, what will happen? It will create a cylindrical shape. That means I am creating 3D cavity with 2D pattern. So that is the meaning of sweep pattern, right? Then follow board pattern. Generally, follow board pattern is not a pattern. It is just a wooden device. There is no use of that. We never use this follow board pattern. We only use split piece pattern, single piece pattern, and gated pattern. split piece, solid piece pattern, and gated pattern most of the times, right? And then come to down what we have, comparison of metallic patterns, right? So it is a good comparison between pattern materials. So what for what advantages we are using the aluminum alloys, and for what disadvantages we are not choosing aluminum. This is the general information. You can pause the video and study this. There is no need of explanation. You can understand it very easily. And the pattern materials based on expected life, right? I said earlier also, we use metallic patterns if we want to produce more number of components, more number of castings. So we use hardwood pattern material for producing more than 200 castings. That means the casting has to be under 600 mm, right? Hardwood pattern is used to produce 200 casting, 2000 castings without using another type of pattern. Just single pattern is used 2000 times, right? 2000 times we can use hardwood pattern if the size is under 600 mm. If the size is 600 to 800 mm, the hardwood pattern can be used only 1000 times. If the size is above 1800 mm, the wood pattern can be used for 500 times only. That means if the size of the casting increases, the number of times that we use the pattern material will get reduced. Well, this is all about the pattern design and allowances. Sorry, I forgot one thing to say. In the shrinkage allowance, the special material is there, that is grey cast iron. It shows a different behavior, that in the stages of liquid and solidification stage of shrinkages, the volume will get increased. Volume increases. Up to now, all the materials, the volume get contracted, right? The volume is decreasing on solidification, but here the grey cast iron will show a different nature, that on solidification the volume will increase. That's why there is no need of designing riser. No need of designing riser. Just it has only solid contraction. So by providing pattern allowance, we can make the product exactly. Because of presence of carbon in free form of graphite flakes in solid stage, there is a possibility of contraction of material. To overcome this, shrinkage allowance is provided. That is what is pattern allowance, that is shrinkage allowance. To overcome the shrinkage allowance is provided. Right? There is no need of designing riser. This is the important objective question in IES exam. Please remember this thing, right? The special material that will increase its volume on cooling, right? I think I covered each and everything that is required for GATE and ES exams, and more than that also. If you like the video, please do like, share, subscribe, and don't forget to comment. Thank you.